Hello everyone, this is Scott from ChemTalk, chemistrytalk.org. Today we're going to look at 16 different reactions with the element magnesium. We're going to test its reducing power against 11 different metal cations in solution and then react it with 5 different acids. During these tests we will see a couple of very interesting surprises I think you will want to stick around for. Now, magnesium is one of my favorite metals because it is highly reactive yet safe to handle and relatively easy and inexpensive to get. I like magnesium ribbon because you can play with it like a slinky and easily break it apart with your fingers. Let's talk about the properties of magnesium for a moment. First isolated by the very prolific chemist Sir Humphrey Davy in 1808, it has atomic number 12 and an atomic number of 24.3. It's in the alkaline earth metals group below beryllium and above calcium. With a density of only 1.7 grams per cubic centimeter, it's one of the lightest of all metals. Only sodium, potassium, lithium, rubidium, and calcium are lighter. I did not know those were the 5 lightest metals, so that's at least one thing that I learned in this experiment. It's even lighter than sulfur. And did you know it makes up 13% of the mass of the Earth? It's also the second most abundant metal in seawater after sodium. Looking at the standard reduction potential table on the ChemTalk website, I saw that magnesium being oxidized to the +2 state has an oxidation potential of 2.37 volts, which means that it is a much stronger reducing agent than any metal other than the other alkaline earth metals. So I was really excited to see how these 16 reactions went. First, we lined up a gauntlet of 11 metal compounds in solution: copper 2 sulfate, cobalt 2 sulfate, nickel sulfate, vanadium 5 sulfate. We made the vanadium 5 sulfate on the spot from vanadium pentoxide, sodium carbonate, and sulfuric acid. Most procedures use a very lengthy process to synthesize ammonium metavanadate, but our shortcut methods seem to work just fine. We also had zinc sulfate, tin 2 chloride, lead 2 nitrate, ferrous sulfate, ferric chloride, sodium tungstate, and sodium molybdate. So what did the reaction with the magnesium ribbon give us? Copper 2 sulfate gave us elemental copper, as was expected. With cobalt, we produced a beautiful blue cobalt hydroxide that fell to the bottom of the test tube. But the magnesium ribbon also turned very black, which means there's either some element or compound that also formed on the magnesium ribbon. There was no visible reaction with nickel sulfate other than some hydrogen gas. Vanadium sulfate gave the most vigorous and dramatic reaction, and it almost bubbled out of the test tube. There was a dramatic color change from yellow to teal blue as vanadium was reduced from +5 to +4. Zinc produced gelatinous zinc hydroxide, but also beautiful crystals of some element or compound on the magnesium ribbon. We need to confirm if it is elemental zinc, but they do look gorgeous. Elemental tin crystals were formed in the tin 2 chloride solution, and you can see the beautiful tin needle crystals in the tube. But in our opinion, the most beautiful result was the elemental lead crystals that looked like a glistening geode filling the test tube. And here you go, you can see the lead. The ferrous sulfate was pretty well oxidized when we purchased it. When we added the magnesium, it turned green, and eventually this mix of iron 2 oxides and hydroxides formed. Ferric chloride actually produced quite a vigorous reaction, producing a large amount of hydrogen gas and eventually formed that tan precipitate of ferric hydroxide. The sodium tungstate did not have much of a visible reaction, but you can see some discoloration on the magnesium ribbon in the test tube. But in the sodium molybdate, the magnesium ribbon turned this dark black color with some yellow spots. So there's definitely 2 different compounds or elements forming on the magnesium strip that we have not been able to identify yet. So let's move on to the acid tests. Like aluminum and many other metals, magnesium has a micro-thin oxide layer called a passivation layer that the acids will have to eat through first. So which acids did we test? We tested adding magnesium ribbon to vinegar, which is 5% acetic acid, 31% hydrochloric acid, 93% sulfuric acid, dilute nitric acid, and 68% azeotropic nitric acid. One of these reactions was quite spectacular, as you will soon find out. So as you can see, the magnesium is reacting with the acetic acid to produce hydrogen gas at a noticeable rate. Moving on to the hydrochloric acid, this was by far the fastest reaction, with the magnesium jumping up and dancing on top of the acid because it was so reactive. Again, hydrogen gas was produced along with gaseous hydrogen chloride. Good thing we did these acid tests outside because there was definitely hydrogen chloride fumes being produced with the hydrogen chloride. Next, we added the magnesium to the sulfuric acid. Interestingly, there was not much reaction in this case. We had produced these results on a different day, and it seems like other people also report not a strong reaction with concentrated sulfuric acid. Perhaps the acid has trouble breaking through the passivation layer of the magnesium oxide. We're really not sure. Anyway, there was not too much reaction there. Next was dilute nitric acid. Now, the dilute nitric acid reacted fairly well, and it produced either hydrogen gas or nitrous oxide, N2O. I've read reports that in certain concentrations, magnesium ribbon and dilute nitric acid can produce nitrous oxide, but I was not able to independently confirm that that was what is being produced in this reaction. One thing I do know is the reaction with nitric acid is quite different. So last but not least, concentrated nitric acid produced a very violent reaction, producing nitric oxide, NO, which instantaneously reacts with oxygen in the air, produced a brown nitrogen dioxide gas that you're seeing here. Nitrogen dioxide is a very toxic gas, and we had prepared for this scenario by moving far back. The good news is that the human nose can detect nitrogen dioxide levels much lower than when it starts to become dangerous. However, even though we moved very far away from this gas, we still caught a whiff of it. This should be an important lesson to anyone considering generating toxic gases, that even outside it is difficult to completely escape them. By the way, did you know that nitrogen dioxide is a liquid below 21 degrees Celsius, basically below room temperature? And did you know that nitrogen dioxide is always in equilibrium with a colorless gas, dinitrogen tetroxide, N2O4? Dinitrogen tetroxide is favored at lower temperatures, while nitrogen dioxide is favored at higher temperatures. There's so many interesting things about this compound. I only had nitrile gloves, which are a good choice with everything we use today except for the nitric acid. Even though the gloves did not come in contact with the nitric acid, the fumes weakened one glove enough so it basically fell apart. However, as you can see, the other glove was still fine. Overall, we were very pleased with how magnesium reacted today and how it surprised us with several of the reactions. What reactions with magnesium have you done or would you like to do? If you learned something today, please give the video a like and subscribe to the channel. Let us know in the comments what further tests you'd like to see. Tell us if you'd like us to further identify any of the products in the test tubes and how you like the video. If we get enough comments, we'll make a follow-up video analyzing some of those compounds. We'll see you soon, and be sure to visit us at chemistrytalk.org.